So we'll talk about programming, multi-threaded programming in Java. And just a little reminder, because it's good to know what's going on behind the scenes. Your operating system, here's an example of an operating system that has three processes running. Process A, Process B, and Process C are all considered ready at the moment. Ready means it's not waiting for any resource, so if you put it on the processor, it would start running. And in this case, our operating system is saying the pointer to the running process is Process B. If Process B has the ability to spawn children, children of a process are considered threads. They're kind of like a separate process, but they're sharing the same resources and storage of its parent. So it's not like it's got its own address space. Threads share the same address space of its parent. So in this case, there's two threads, let's say thread 1 and thread 2. And when process B is running, the operating system allows thread 1 to run for a little while and then thread 2 to run for a little while. And inside the process, there is kind of a mini ready queue and running pointer. So basically, this thing runs, and then after that in the linked list is this one, and then it goes back to the first one. So they just keep cycling through. And like we said, the parent could run while the children are running, or the parent could suspend itself if it wanted to. So now, depending on your programming language, you have to know how to write code that will allow your program to split into children programs. So the way Java decided to allow multi-threaded programming is they have a class called thread. And then you can create objects that extend from thread. And if you create an object that extends from thread, it has the ability to go on and be a thread. So in this case, we're making a class called myThread, and we're going to say it extends the Java class thread. And then in this case, I have, so what is this now? Just a little Java reminder. If you have a method that has the same name of the class, what kind of method?
Constructor.
Constructor. So this is a constructor that takes in no parameters. So just a little review on Java. Do you remember if you create a constructor that takes in a parameter, what happens? Well, what if you have no constructors? What happens?
It sets the default constructor by itself.
Right, which is basically this. I take in no parameters and I don't do anything. Right? So this is kind of, I'm rewriting the default constructor. Right? Do you know what happens in Java if you create a constructor that takes in a parameter and does something? Do you know what happens to the default constructor? Is it still there, or
It's still there.
it's still there, or it goes away?
I thought it was still there, as long as, like, if you pass it something, no parameter, it would just go to its default.
It'll use the default one instead of the one.
Even if you give a...
I think if you give both the default constructor and the other constructor, it will still do the default constructor if you don't enter.
Right, you would have to say it, because in C++ you get a default constructor and it's always there, and you can add more if you want, but in Java they take it away. If you give a constructor with parameters, then the default one will go away unless you bring it back and redeclare it yourself. So I just didn't want that to be confusing code. But anyway, so I have two constructors, the default constructor which does nothing, and then I have one where you can pass in a string, and then I call super. Does that, remember that, calling super? So you're calling the class above you, the one you inherit from, and passing in the string. So we could set the thread's name that way, and we could even output it. Okay, so now we have a method. This is a special name for a method in Java. Inside a class, inside a thread class, if you have a method called run, that's going to end up being a special name. The run method is where you can put code in it that will run on a separate thread. It's the only method. If you have any other method, it's probably bookkeeping about the thread, but it's to be used only by the parent process. But if you happen to pick a method called run, that one has the ability to be spawned onto a separate thread and run. So then you might think, what if somebody just accidentally picked a method called run? You can make up any name you want, and then ran it, and they didn't want it to be run as a separate thread. So The mechanism is, if you would like the code that's in the run method to be run as a child of the parent, you don't call run, you call a method called start, S-T-A-R-T. And that's a special method in Java, which the code of that start method is it does the operating system work to create the child thread, and then lets whatever the body of the run method, it runs the run method on the child thread. So if I was to write out the code for the start methods, line 1 I'd write in like English, I'd say create the child thread, and then step 2, run the run method on that thread. So in this example, I try to keep this as simple as it can be. We need to have a main section. So we have our outer class, this is example number 0. And what I'm doing here is I'm saying I'm creating an object of type thread. I'm allocating it new, so it has to be on the heap storage. So I'm going to allocate this, and it will stay in effect until the garbage collection comes and takes it away. And I'm going to say it's of type thread, and then I'm going to pass in a new thread, and I'm going to call it my thread number 1. So in this case, I'm using the default constructor and then passing in a name, the name my thread number 1. For thread number 2, just for fun, I'm making thread number 2, I'm saying it's new, and I'm calling my thread, and I'm passing in the string. So this is the constructor that actually takes in a string. And this string is then being passed up to object and being written as the thread name. So both of these are doing the same thing. I'm just writing the name of the thread. Just 2 different ways of writing the name of the thread. So this is the declaration and the storage allocation for the threads. They haven't actually started yet. And now what I'm going to do is I'm going to start the 2 threads. I'm going to say thread 1 start. So when I call the start method, now you might say, well, we didn't write a start method. Where did it come from? And it comes from object. I'm sorry, it comes from the thread class. So this method will create, so what you're looking at, this is the main method. This is the parent. This is the parent process. But what we're doing is we're saying that thread 1, I'm going to call for thread 1, I'm going to call start. So the parent is now creating a child thread, a child process. And then it's going to run, if there is a run method in the class, it's going to run the code of the run method on that child process. Now, we don't have to wait for this to finish before we can go to the next line, because this is running on a separate child. If this was run on the parent, we'd have to wait for this to finish before we can go to this one. But because this is the special method, the one that creates a child thread and lets it start running, it just goes to the next process. So then we call start for process 2, and that one's running. And then we, at the end, but it'll never end, oh no, this would be part of the parent. The parent can print out what the current thread is. At any point in time, because you can now create many objects with the same code, you might want to get confused which thread is running. So at any point, you can say print out the current thread. So there's many methods that come with thread, and one of them is current thread. So if we were to compile this and run this code, what do you think the output would look like? So we're doing a print line. We're saying the current thread get its name, which is what we're setting here, and just say that thread is that thread running. So what do you think it would, and the other thing is, I'm doing a while true. So when is true true? It's always true, right? So this will just keep happening forever. So what would you expect the output of this to be? Yeah.
It'll just be a bunch of thread 1 running, thread 2 running.
And like, will it?
It won't alternate perfectly, but like.
Yeah. So it's really up to the operating system to say how long thread 1. Maybe thread 1 would run first, because we called it first. You'd hope that one would get the head start. But it'll run for a certain amount of time, and the operating system will say, okay, that thread is done, and let the other one run. So it's going to be kind of like this. Thread 1 will run for a little while, and then thread 2 runs, and then thread 1, it'll just be doing this for a while. And what is this thing doing? It's just printing out. What its thread name is. So if we were to compile this, so if you remember, there's nothing fancy you have to do when you're compiling multi-threaded programming. In C++, just a little side note, you would do, you'd say the compiler's name and the file's name. Since multi-threaded programming came after the C++ language was created, you have to actually put an option here. If you're using POSIX thread, you'd have to say -p threads, and that way you're saying, tell the compiler to use the special multi-threaded programming package, which came later. But the Java programming language included multi-threaded in the language, so you just have to compile it. So I'm just compiling example 0.java, and hopefully this compiles. Okay, and then to run it, let me run Java again. Get rid of the C, right? Java, and then the class name. So this runs. I want to try to. Okay, so and yeah, so I left it in an infinite loop. So okay, so one thing, this is now running. It's running so fast you can hardly read it, but it's kind of like what you said. Thread 1 is running and saying it's running, then thread 2 runs for a certain amount of time. If I wanted to stop a program that's in an infinite loop, what would you have? How would you do that? Have you ever had a program go in an infinite loop like this? And you say, how do I stop this thing? So what do you do?
Windows, it's Control-C. Linux, it's Control-Break.
Control-Break? Not Control-C?
I think
Because this is a Linux.
Is it? I think it is Control-C.
Okay, right. So really, what is actually happening? This is kind of a multi-threaded question on top of a multi-threaded question, but I'm going to try. Did you say Control-Break? What's break? Can't even find the break key. But let me try Control-C. Okay.
I think you just mean smash the tower.
What's that?
What? No.
Oh, okay. Yeah, just bang on top of the tower, right? But anyway, so what was an interesting question is, I just hit Control-C, and this is a Linux, this is Rockhopper, so this is a Linux system. So really what was happening, we can now look up, so this was going pretty quickly. This, whoa. Okay, so I'm scrolling up. What I'm doing here is I'm scrolling up, and as I'm scrolling up, I found the point where it switched from process thread 2 to thread 1. So basically it was just saying thread 2 running, and then eventually it timed out. And now it started saying thread 1 running, thread 1 running. So when I eventually hit at a certain point, because the two children threads were just going to run forever. So when I hit the bottom, when I hit Control-C, what actually happened? So now you guys are getting good at operating systems and multi-threaded programming. What actually happened? Like a parent killed a child. What actually happened when I hit Control-C? Because it caused everything to stop.
Killed the whole process?
So what is the parent of what here? So this is actually a shell, right? When you bring up an external, that's actually a process. And then from that process, I ran example 0, which created like kind of a child process. And then example 0 had its children. So it's almost like
Generations.
yeah, it's like grandchildren. The thread 1 and thread 2 is kind of the grandchild of the shell. The shell had a child called example 0, and then that had children. And from the shell, I hit Control-C, which caused the parent to get killed, which killed the children. There's one of the control something else would kill the parent only and let the children keep running, or children could be running in the background. But so yeah, so in this case, like you said, that was a good guess. So it was printing, 1 is running, and eventually the operating system times that thread out and lets the second thread run, and then that one started running. And how often it runs is really at the mercy of the operating system. So we might want to have examples where we have more control over which one's running and which one isn't. And so what I'll do is I'll go over an example where, and I hope I didn't complicate this too much, but I have a class called Producer Consumer Java. So what this code is doing, so basically there's a classic operating systems question, a producer-consumer question, which we've talked about in the past. where we have a thread that is considered a producer. So it's producing something. Maybe you're sending pages to a printer, so it sends, here's page 1, and then tells the printer to print that page. And then it says, and then after the printer says, I printed that one, now we load page 2 and say, go print it. And then we load page 3. So we wouldn't want to have the processor, the producing process to go, here's page 1, and then on top of that is page 2, and on top of that is page 3, and then the printer prints page 3 8 times. We don't want that to happen. So we'd like to have some coordination between printing and not printing. So in this case, I have so now in this case, so that's kind of a simple example where we have one producer and one consumer. You might want to have many producers and many consumers, and they're writing to a shared area that they all have access to. So in this example, we have a producer, producer-consumer class. It contains a linked list, which is coming from the Java containers. We'll have a linked list of 10 items, and we'll have a variable called done as full. So now we have a class called producer, which extends thread, and we want to have a run method. So the run method will be, code for the run method will do this. The run method will, just like the last time, it'll be a runaway train. It'll do this forever. It's going to go and get something from the network, and that's going to be written to an area called just produce. So there's some object we're producing. And then what we'd like to do, instead of just having it run like out of control, we're going to use Java's synchronized keyword. So we're going to synchronize on the list. So synchronized for an object says if some other thread is trying to access this same object, but one thread already has access to it in a synchronized way, then from this open paren down to the corresponding close paren, any other thread that wants access to list will have to wait. So this synchronized thing, from the beginning of this open paren to the end, it's kind of like this is doing the Dijkstra's P operation, P of list. So list you can kind of think of as the semaphore, but it's actually an object. So all objects have a built-in semaphore and thread queue for it. So the synchronize, if this works successfully, then that means this thread has access to the list and has blocked out anybody behind it. And as soon as we get to the corresponding close paren, it's like it issued the V command and woke up anything that happens to be waiting for it. So now we're saying while, what are we doing? While the queue is maxed out, we'll keep trying, we'll say that the producer is waiting. And anytime we're going to do a wait, we're going to have a catch for it. So we'll say that we're waiting. So this would be the case where one of our many producers is trying to push something into the buffer that a consumer would take away. And if the buffer is full, we're now going to call the wait routine, which is also going to put ourselves to sleep. And hopefully someone will wake us up at some future point. Once we then wake up, we can say add something that's been just produced. And then we do a notify, we'll do a notify all to tell all the consumers you can come and get this. And then if we're eventually done, we have a variable called done, we can break out of this infinite loop. So then we can get requests from the network. So this is a routine that's getting the object, the producer's getting it from the object. So this, we have our thread go to sleep for 10/1000th of a second. So we'll pick, that's just going to simulate some time passing by while we're trying to read from the network. And if anything goes wrong, we'll say the producer had a read interrupt. And then we return some new object. So we're taking some new object and returning it, and that's what's going into our buffer of 10 spaces. So this is just, a routine that's simulating like the producer went out and produced something and then put it in our shared buffer that the producers and the consumers are reading from. Okay, so now we'll have a consumer class. And consumer extends from threads, so that means it has the ability to run on a separate thread. And we have a run routine. The run routine will loop forever. And we're also doing a synchronize on the same object, the list. So now the question is, if a producer or a consumer, and in this example we're going to have many producers and many consumers, if any of them want to read from this one shared list of 10 items, if anyone wants to read or write from it, they're going to queue up to read and write from. So the queuing up, what we're doing from your operating systems class, you remember there's the P function and the B function. The P means, you know, I want access to this resource and I want to block everyone behind me until I declare that I'm done. So in Java, you don't say P of list, you say synchronize on list. And it starts at the open paren and ends at the corresponding close paren. So it's kind of like there's a V of list right here and a P of list right there. And list is a binary semaphore, so either you get it or you don't. It's not a counting semaphore. So now we're saying while the list is not 0, so this is now a consumer. So a consumer wants to just grab something from the list and consume it, take it away. If the list is 0, then that means the consumer went to consume something, but there's nothing to consume, so it might as well go to sleep. So what we'll do is we'll say on the list we'll do a wait, which means it'll wait there until somebody notifies it, and then the notify will take it off the wait list and put it back on the ready queue and start running again. And then what we do once we're awake, that means now there is something in the list to run. We'll call the remove the last one object and then notify everybody that the list is open again. Okay, so I hope, you know, like I say, I hope I didn't overcomplicate this. I could have done a simple, you know, one producer, one consumer, but what I'm basically saying here is I'm creating producers and consumers, the number of producers and the number of consumers. And what I'm now doing is, so what we saw in the last example, you could say for an object called the start method. Well, we could put that in a loop, right? We could create an array of, we can create an array of threads and then just say I equals 0 to the number of threads, start them all up. So there's no cap on how many threads we could run. So let me just see how many threads we decided to have. Gotta count somewhere. Where is oh, okay. Yeah, the counts it down here. Okay, so this is a routine producer consumers. This is just this will start them all up. And what I'm doing is I'm saying the number of producers is 4, the number of consumers is 3. You can change those numbers to whatever you want. And now I'm saying I'm making a producer-consumer object of type producer prod cons. And I'm calling prod cons and I'm passing in the number of producers and the number of consumers. So I'm now going to create one of these objects and I'm passing in 4 and 3 here. And what this is going to do is it's going to call the producer start method on all 4 producers, and it's going to call the start method on all 3 consumers. So what we basically are going to have is 4 consumer processes running constantly. And what do those things do? They read something from the network, which is our fake routine that just creates an object and writes it to an array. If it goes to write it to the array, but the array is full because the array had 10 spots, it'll go to sleep until the consumer takes something and notifies us there's now room to write something to. And so we will kick off all 7 threads. They'll all start running. The consumers will try to read something from the linked list, but if the linked list ever shrunk down to size 0, then there's nothing to read, so it goes to sleep and waits for a producer to produce something and then wakes it up. And we do this until it's done. Let's see if I can make this thing sleep. Oh, it goes to sleep for 10 seconds. And then it tries to, the parent thread tries to synchronize on the list. And it marks the variable done to be true. And then notifies everybody to wake up. And so each of the, hopefully, each of the consumers, yeah, so The consumer process, I have code here that says if done is true, then break out of this infinite loop. So eventually, all 7 children will be done running. So if you had to describe in English, what do you expect the output of this to be? So the way this code is written is we have 7 processes, 4 producers, 3 consumers. They're all going to run in infinite loops. So the parent's going to kick off 7 threads, 4 producers, 3 consumers. And the producers will keep trying to grab something and stuff it into the shared buffer, which has 10 slots. And it's a linked list, so it will grow and then shrink. Will be, you know, I don't know if you remember from Java, the linked list grows and shrinks as you add to the end of it. So the consumers will come and try to read from the beginning of the list, but if there's nothing there, they'll wait for something to be there, then they'll wake up and try to take it. So if you just had to, I don't know, describe the output, what do you think it would be? They all should be printing, hopefully, oh, I should have put the thread number down. Consumer waiting. And I'm constantly printing out the list size every time something happens. So, yeah, so what would you expect the output of this to be?
I should have.
You know what, maybe I should have put which thread is saying this. Producer waiting. You know what? Okay. Well, yeah. Let me first run this, and then what we could do is if the code isn't so meaningful, we'll add more code to it. But anyway, if I compile this, this would be. That's the name. Okay, these are warnings. These are, so we can still run the code with these warnings. But what would you expect the anyone have an expectation for the output? So each of when the processes got stuck, so if they're not, I didn't print anything out while it's consuming or producing. I only wrote when it went into a wait. So it says I'm waiting and then it kind of wakes up again. And it kept printing each time a producer or consumer ran. It kept telling you what the size of the buffer, which could be anywhere from 0 to 10 was. But I'm hoping that the queue would build up, but let's run it anyway. And then the other thing is after 10 seconds, the parent thread kicks off the 7 processes. The parent thread is still running. The parent thread doesn't stop and wait for the children to come back. So the parent thread kept running. So we really have 8 threads running. The 7 children plus the parent are all sharing time. And then what I did here was I said 10 times 1,000. So 1,000 is in milliseconds, so this ends up being 10 seconds. I could have said sleep for 10,000, which would have been 10 seconds, but I'm just kind of spelling out that I'm doing 10 seconds. After 10 seconds, the parent process will wake up, and then it synchronizes on list and sets the variable done to true, which will then cause all the children the next time they run to break out of their infinite loop. So after 10 seconds, everything should come to a rest. So if I go to run this, so hopefully this runs for 10 seconds and stops. Okay, so now we can kind of see something. Producer 1 seems to be doing all the work. But anyway, so what's happening is the code is basically we had 4 producers. The producers were actually taking time to go and build something and then put it in the queue. The consumers this I actually find odd. The consumers, remember we have 3 consumers. So at any point in time, all 3 consumers can run and say there's nothing to consume, so I'll put myself to sleep. And that's what these are. These messages they print out right before they go to sleep. So I'd expect all 3 consumers to say, I'm going to sleep, I'm going to sleep, I'm going to sleep, but I would expect 3, not more than 3. This could just be a timing issue. And then when a producer produces something, it notifies all the consumers that they could wake up. I'd figure one would wake up, consume the thing, and then go back to sleep. So it looks like the producer produces one item, which makes the list size of size 1. Immediately what's happening, yeah?
I think the problem is you're doing notify all, not notify all.
Right. So by doing notify all, they're all waking up. Then they're all going to go back to sleep, right? But I guess the question I'm asking, it must be just a timing thing. When a producer produces something, the list size goes up to 1, then all the consumers are woken up. It's like a free-for-all. The first one to grab it gets it, and then the rest of them. The first one to grab it takes the thing, reduces the list size down to 0, which will cause that one, because it's in an infinite loop, plus all the other ones when they run to go into back to sleep. So I would have thought it would go, every time something got produced, the count would go up by 1. And then I was kind of hoping it might produce 2 or 3 things at once, and then wake up like 3 of them, and all 3 would get consumed. It looks like the amount of time it takes to produce something eats up the whole time quantum for that thread. So it can only produce one thing, and then it goes back to sleep. Then I would expect all 3 consumers to wake up. The first one would consume it, knock the count down to 0. So that's this message. This message is saying the count now went back down to 0. And then that consumer then runs again and realizes there's nothing to consume, so it puts itself to sleep. The other ones have woken up and they would immediately put themselves to sleep. So I think there's just a delay here, because this is the message of the object being consumed. It's possible that this going to sleep is one that happened on a thread before while the producer was running. But I did think that there would be exactly 3 consumers going to sleep every time something got produced. They'd all wake up and then all go back to sleep. And it looks like we got 2 here and 1 here, and then sometimes 5 here. So it might just be a timing thing, that some of these are going to sleep from before an object was produced. Okay. So yeah, so like I'm saying, it's just, really what's happening, it's just kind of, this is the multi-threaded programming. It's good to just know what's going on behind the scenes, and then in your language how to make that happen. But what we're really doing is we just have a parent process. It's kicking off a child and another child. Actually, you know what, I should have had like the colors change from parent to child 1 to child 2 back to the parent. The parent could kick off a child thread if it wanted to and have the parent be suspended, so the parent is not wasting any time. If, let's say, the child thread had to produce some value before the parent could even go ahead, then there's no point in the parent running. The parent would be taking up time and not taking up time in the processor and not doing anything. So the parent has the option to wait while it spawns one of its children, and also the parent has the option to not wait and have the child run and share the time with the parent. And so, for example, when we go over, we'll talk about Linux later on in the course, but if you've ever brought up a shell, you ever bring up a shell and you type a command, once you type in that one command, while it's running, the shell can't do anything else, right? Except if, I don't know if you've ever typed in a command and then put an ampersand on the end of it. What you're doing there is saying, I want this process to run as a child, but I want the parent to still be sharing the processes, so the parent can do other commands too. Okay. So yeah, so what we covered in the second example, the first example was just, code running, threads running, and just 2 threads running doing completely independent work of each other. And in this case, we had to introduce the idea that the threads, the producer thread, is writing to a list. So it's basically saying, you know, add first. So let me find the add first now. Where's add first? Oh, here's add first. So, yeah, so basically what's happening is that both the producer and the consumer, all in this case 7 processes, are reading and writing from the same shared list. And in order to do that, before you write to the list, you don't want one reading it while another one is writing it at the same time. So we need to somehow lock them out, and in Java we have the synchronized keyword. And you do a synchronize on a particular object. So inside our method, we could do a synchronize on one object, and then a synchronize on a different object. And we could also put ourselves into a deadlock. If you synchronize on A, and then within that bracket, you do a synchronize on B, and another thread is synchronizing on B first, and then on A, those 2 threads would go into a deadlock. So we want to be careful about how we use those. And then the other thing is you could do a synchronize and then have so much work that's in here, you'd be blocking out all your threads for a very long period of time. But it wouldn't be indefinite, but you have the ability to do it for a very long period of time.